380 nanometers will be cut off by the lens. Now in general, when you think of wavelength under 380 or 300 nanometers, what kind of light do you think of that as? Infrared on the other end. Sorry? Very good. This is ultraviolet light, right? So blue light. Blue light in general, not good for living systems. Right? I mean, you hear this all the time, right? You go out in the sun, you want to put some protective cream and so on and so forth, which will try to reflect UV light away. So UV light in general is damaging. In fact, it kills cells. Right? You don't want that going through directly onto your photoreceptors because it will kill the retina. Right? So you have built-in mechanisms in order to actually reject all the UV light going through. So the first layer is the cornea. The second protection layer is the lens itself. Okay? Now, the retina in general will receive light within the range of 380 to 950 nanometers. Right? So this is the visual range we sense in, 380 being blue, 950 being infrared light. Right? So IR. Now, of course, as the lens ages, it's going to change its transmittance. Okay? So it becomes yellowish in color. Right? As we get very old, you have heard the term cataracts. Right? Cataract is nothing but the complete yellowing of the lens where the transmittance power drops so low that there is very little light going through. Right? So that's when one may talk about lens replacements and things like that. Anyway, but the visible range that we typically care for is within the range of 380 to 770 nanometers. That's our typical transmittance range where we have, pretty high transmittance. Your transmittance curve, by the way, is not flat. Right? You don't send every wavelength of light equally through. Okay? So the transmittance curves of the lens and the cornea vary according to wavelengths. If we talk about white light, about 70 to 85% of white light normally is transmitted through to the retina. Okay? So what is white light? Sorry? All the colors, very good. So for us, normally when we think of white light, when we talk about lens systems and we talk about white light, it's essentially the integral over the sensing wavelength range that we are talking about, right? So if we talk about visible 380 to 770 nanometers, it has all the three colors. You integrate over all the transmittance of those wavelengths, you get an integral of what light goes through and what we call white light. Right? Equal proportions of all integrated over through the transmittance curve. Okay? Now the photoreceptors will all sense the wavelengths coming through. Now photoreceptors in fact are fairly protected. Okay? So it turns out that if you think of a camera, right, you have photoreceptors right on the chip. Right? So you have a lens system in front, you have light coming through and it falls on the chip, it gets charged and the charges transmit, they're digitized and you get an image. Right? Well, the human vision system is not quite the same. The photoreceptors are not there front facing to actually see the light coming through. In fact, it turns out that they are buried several layers behind on the retina and they're actually backward facing. So the light has to traverse through several neurons in order to get back to the photoreceptors, turn around and get sensed by the photoreceptors. Okay. This is the way the retinal layers are constructed. And it's a way for the vision system to protect the photoreceptors from failing, okay, for all kinds of reasons. Now the receptors actually come in two shapes. Okay. They're literally different shapes. One of them is more conical in shape and we call them cones. The other is more cylindrical. We call them rods. Okay. So they each have different functions to play as well. Rods are basically used for low light sensing. and rods are unable to differentiate between any color. Okay? All it can sense is raw power, right? Raw integral of energy coming through across any wavelength of light. It cannot differentiate between wavelengths. Cones, on the other hand, are what we call our color photoreceptors. Okay? They come in 3 flavors: red, green, and blue. That's what we call them because that's how we think of, separation of colors in a continuous spectrum of light. Okay? So the cones are generally the ones that are active or predominantly used for color sensing or daylight sensing. Okay? Our color sensing capability at night is very poor. You don't see colors very well in low light situations. And that's because the cones are not the primary photoreceptors in low light environments. It's the rods they are. And the rods don't see color very well. Okay? They don't differentiate at all, in fact. Okay. The rods themselves tend to be very small. They're 1 to 2 microns in diameter. Cones are slightly bigger. They're 2 to 3 microns in diameter. Okay. Now, cones are extremely concentrated and densely packed at the fovea. Okay. Fovea is the region around your optic axis. Okay. The point where the optic axis intersects the retina is your fovea. And a narrow region around the fovea is where all the cones are densely packed. Okay. As you go away from that, the packing density drops dramatically for cones. Beyond about 20 degrees, it kind of stops. You have rods all over. Okay. There are no rods in the fovea at all. Okay. Their density increases away from the fovea, and then it becomes fairly sparse as you go towards the periphery of the retina. So as a result, if you think of it, the density is representative of what? Ability to perceive color, yes, but what else?
I think it sort of defines focus.
Very good.
Around it you'll perceive more contrast and silhouette.
Yes.
Where in the center you'll perceive more detail because it's more color.
Very good. So detail. What does detail translate to? Not just amount of light, but remember that the packing density of cones, right? Having a lot of cones, what does that amount to? Resolution. Very good, right? Detail, resolution. So it amounts to very high resolution. So if you look at the retinal structure, it turns out that we don't actually have a constant resolution when we see things. It doesn't seem like it, right, when you look around. But that's what it is. We do not see everything around us at the same resolution. We only see details or the highest resolution when we are looking straight at an object. You can try this, right? I mean, you can look at, at least for you guys who are sitting closer up front, I don't know how well it would work for you further back, but if you look at the screen here and try to read the text, as you read the text, shift your eyes away from it and see if you can still keep reading it. Right? You will see the shades on the periphery. You can see the contrast changes. You can see the blacks, the whites, but you can't read it. You lose the ability to see that detail. Right? That's because we do not have the same resolution away from the fovea, the central point of fixation. That's also the reason why anytime you want to look at something small, what do? You bring it right in front of you as close as possible, because that's when you will see the detail. That's where you get the best sampling. Now, on the other hand, how many of you have ever looked at stars, used telescopes